Just to kind of remind us where we left off, we were dividing polynomials by other polynomials, this process of long division. And I think kind of one of the few new pieces that we added to this was this idea that once we do this division, once we get our thing that we get when we do division, we get the thing that we divided by, and the remainder, we can reconstruct the original polynomial by taking the thing that the division gave us times the thing that we are dividing by plus whatever the remainder is. And we saw, well, really, this is something that we could have been doing with division all along. We probably haven't really done this with division ever before, but we'll see kind of this suitability within polynomials that will make this very, very nice. Now, I want to kind of draw our focus towards this thing that we are dividing by. In this case, for the first example that we looked at yesterday, it was this 3x minus 2. And I want this to kind of look very, very similar to really what we have been doing up until this point, where we have been taking our polynomials and writing them out as kind of a product of their zeros. So like x minus k1 times x minus k2, so on and so forth. Of course, the difference here is that we don't just have a bunch of zeros being multiplied together. We also have this plus 1, which actually does kind of create some complications that would otherwise make this process really nice. But I do kind of want to think of this 3x minus 2 as being very similar to one of these roots. And to that end, if we are thinking about, obviously in this case, not the 0 that corresponds with it, but the value of x that kind of would correspond to something like this 3x minus 2. If this were a 0, what value of x would we kind of gain from what we see here? In other words, what is the value of x that makes this not quite a root, but kind of like a root 0? 2 over 3. Very good. 2/3. All right. Now, obviously, this isn't going to be a 0 again because of this plus 1 here, but we still could certainly ask the question, what is going on with our function when we are equal to this 2/3? This is kind of back from our original equation, and certainly we could take this 2/3 and plug it through all of this. We could cube it and then multiply it by 6, and then square it and multiply it by 11. Find all those kind of common denominators, add it up. It's a very long, pretty laborious process. But having done this kind of division, notice that what will be a lot easier is actually plugging it into this division algorithm form. Why is this going to make things a lot easier? Well, when we try to do so, we get 2 times 2/3 squared. Okay, this isn't really looking all that much easier just yet. Plus 5 times 2/3 minus 7 times 3 times 2/3 minus 2, all plus 1. What is this 3 times 2/3 minus 2 going to become? Yeah, it's just 0. And so I have something, don't really quite know what this value is, times 0. Anything times 0 is just 0. And so what are we left with? 1. What was 1? What was the significance of 1 here? It was the remainder from our original division. Okay, so here is what we are going to call the remainder theorem. Right? It's got a little bit of a complicated setup, but we've just really basically seen it in action. All right, let's take our function, f of x, and we're going to divide it by x minus. Right? Now, c in this case, just some random number. This could be x minus 2. This could be x minus 7. We'll see what the value of c actually gives us or how we might find that. This is going to give us, we already know, some kind of answer, d of x, with a remainder of r of x. This is just like basic. If I divide my function by anything, I'm going to get the answer to the division with a remainder. Right? That's just kind of our very basic premise. And by our division algorithm, we are saying that we can set this up to say that f of x is equal to this thing that we got, this d of x, which we're going to see doesn't matter at all, times x minus c plus whatever our remainder is. And so where does the remainder theorem come in? Well, the remainder theorem says what happens when I plug c into my function. Yeah, it's just going to leave behind the remainder. Exactly. This is going to become d of c times 0 plus r of c. And d of c times 0 is just 0. We get that our function evaluated at c is the exact same thing as the remainder evaluated at c. Now, remember, our remainder can be a function of x. We saw a remainder yesterday. That was a function of x. But as long as this thing that we're dividing by is a linear term, this remainder is just going to be some kind of number. All right, so there might be an instance where you would have to plug back into your function to kind of see what's going on there. But for the most part, this would just be a number. Yes. That our function evaluated at c is the same thing as our remainder evaluated at c. Like 1 evaluated at 2/3, which is just 1. It's just going to be the remainder. It's basically just going to be the remainder. Okay, so let's see this in action. Looking at 1a, we are trying to find our function evaluated at 2, where our function is x to the 4th minus 9x squared plus 14. If we are looking for what is our function evaluated at 2, what should we divide our polynomial by in order to use this remainder theorem? X minus 2, exactly. So we're going to take x minus 2. We are dividing into x to the 4th. Remember your little placeholders. So plus 0x cubed minus 9x squared plus 0x plus 14. This one has quite a few, or a couple of placeholders. How do I match x to the 4th? X cubed. So I get x to the 4th minus 2x cubed. We are subtracting this. 0x cubed minus negative 2x cubed is going to give me positive 2x cubed, dropping everything else down. How do I match x to 2x cubed? I want in this case, because we're trying to match it, it'll be a positive 2x squared. And so we got 2x cubed here minus 4x squared. We are subtracting, of course, get 0. Negative 9x squared minus negative 4x squared is going to give me negative 5x squared. Very good. Plus 0x plus 14. How do I match x to negative 5x squared? Negative 5x plus 10x. We are subtracting still. We get 0. 0x minus 10x is, I got negative 10x plus 14. How do I match x to negative 10x? That's a negative 10. This is negative 10x plus 20. we get 0, and then 14 minus 20 is -6. And so what is that? First of all, what is this -6? This is our remainder. We can't match x to -6. And so what is our function evaluated at 2 going to be? -6. Right? Because you could then construct like, oh, this is going to be x minus 2 times this whole thing plus -6 minus 6, plug into that x minus 2 times whatever piece goes to 0, you're left with just -6. All right, what do we notice about this process? What else could we have done? We just plugged 2 into our function, right? We could have just gone ahead and said, well, f of 2 is going to be equal to 2 to the power of 4, that's 16, minus 9 times 2 squared, that's going to be 36, plus 14, that gives me -6. How long did that take versus what we did here with the long division? It's like the difference between like a 3-minute problem where we're doing a bunch of steps that all have the opportunity for mistake, and the difference between doing like a 15-second problem that's pretty much routine. Now you could make an argument, certainly, that maybe when we're plugging in like fractions, like over here, maybe plugging 2/3 into this actually would be kind of hard to then simplify down to 1. That certainly might be the case. But again, oftentimes this kind of long division process is going to be harder, or maybe not harder, but longer than what it might take to just like plug our function or plug our value into our function. So the remainder theorem is cool. It's not really one that I think has a whole lot of practical application to use kind of directly. Remainder theorem, for the sake of remainder theorem, is not particularly, I think, exciting. It is a longer way to do something that is already not that difficult to do. And so as far as like a tool to add to our kind of toolkit, I'd say this is a pretty bad one. Doesn't do a whole lot for us. What this is going to do, though, why we must talk about the remainder theorem, is for a very special case of the remainder theorem, which is what happens when that remainder is 0. What happens when we do this division and don't have a remainder, right? So we could try this. This ultimately is going to lead us to the factor theorem, which is kind of hard to put into words. It's like this is kind of the gist of the remainder theorem, but like, what do I actually write for a remainder theorem? Don't worry too much about it. It's just this idea of when I divide by this x minus c, then f of c r c. Yeah. Your remainder is 0. Yeah, basically, yeah. That's what we're ultimately going to find. Absolutely, that when the remainder is 0, the thing that we are dividing in is a factor of our polynomial, and if it's a factor of our polynomial, then it is a 0 of our polynomial. Yeah, that's basically spoilers, but yes, that is ultimately what we get. But to just kind of show that, when we do this f of x divided by x minus c, we still get some kind of d of x. Now we're saying we want to assume that our remainder is 0. By our factor theorem, then, what is f of c? It's 0. It's equal to the remainder evaluated at c, which is just 0. And so, therefore, what must be true about the value of c? C is it's a 0. It's a factor, it's a root, it's an x-intercept, whatever. In this particular case, we might say the value of c is a 0 of our polynomial, which is really ultimately what we are trying to look for. We have been looking at in 3.3 how multiplicity can really kind of help us when we have that factored form, when we see all those zeros, help us to kind of piece together what our function is going to look like. And so this ability to find zeros, this ability to find roots, to find factors, is going to be one that's really, really nice. This actually does even more for us than that, though, and that is particularly when it comes to how this relates to taking our function f of x and rewriting this as d of x times this factor x minus c. Because what we are going to find is that d of x is still a polynomial, but it is specifically a polynomial with a lower degree than f of x, which is great because we, as far as everything is concerned, can only really reasonably factor or find the zeros of quadratics. We looked in this class at the cubic formula, and it was a nightmare and it was terrifying. I promised you that there was a quartic or a fourth degree formula. We're not going to look at it. It's even worse. Really, the quadratic formula is kind of the bread and butter of what we have to solve for the zeros of polynomials. And so what we're going to find is the factor theorem, yes, is useful because it tells us that, hey, when we divide by these factors, that they represent the roots of zeros, and that's cool. Really what it's going to be helpful for, though, is reducing the degree of our polynomial so that we can actually work with a quadratic. Okay, so let's see this in action. Looking at example 2a, we are trying to find not just one zero, but all of the zeros for our polynomial, given that one of them is 1. Or, in other words, given that x minus 1 is a factor of our polynomial. Right. 2, -9, 13, -6. Okay. So we are told that x minus 1 is a factor or divides evenly into our cubic polynomial 2x cubed minus 9x squared, plus 13, yeah, plus 13x minus 6. What remainder should we get if we do this correctly? If x minus 1 is in fact a factor, we should get a remainder of 0. So that's just kind of a nice way to gut check ourselves. Again, that's not really the useful bit. The useful bit is what's going to happen to our d of x. So how do I match x to 2x cubed? 2x squared. This is 2x cubed minus 2x squared. We are subtracting. Negative 9x squared minus negative 2x squared is negative 7x squared. How do I match x to negative 7x squared? Negative 7x. Subtracting. 13x minus, 13x minus 7x is going to give us 6x. And then how do I match x to 6x? With a positive 6, 6x minus 6, which gives me a remainder of 0. Excellent. So yes, in fact, x minus 1 is a factor, but more important than that, we can now rewrite our original cubic as x minus 1 times 2x squared minus 7x plus 6. And we go from a problem that we can't really approach, a problem that we can't really solve, to a problem that we've solved tons of times. What are two numbers? 2 times 6 is 12. What are two numbers that multiply to make 12 that add to make -7? 3 and 4. I'm going to, we'll go ahead and show the full thing here. So 2x squared minus 3x minus 4x plus 6 We're going to do our factoring magic here. It's x minus 1, just kind of staying out to the front. This is x times 2x minus 3 minus 2 times 2x minus 3. And I get x minus 1 times 2x minus 3 times x minus 2. And so what are my three zeros here? 1, 3 over 2, and 2. Okay, so the remainder theorem on its own, not very useful. The remainder theorem as a stepping stone to give us the factor theorem allows us to take polynomials that we before weren't really able to touch and now fully break them apart with the zeros, provided that we know a starting point, provided that we know at least one zero. What we are going to do tomorrow is we are going to say, well, what if we don't know any of the zeros? Can we find a way to start there? And the answer is yes, and it's called the rational zero theorem, and it is a mess. And the process itself ends up being wildly, I think a good word for it is frustrating. So we will talk about all of that tomorrow, how to just start from nothing and end up with this. And then fundamental theorem of algebra, which is kind of a thing that we've really already been talking about. And then one kind of final piece, complex conjugate, and then that will be that. But any questions with our factor theorem? Yeah, exactly. So where C is a zero. So yeah, that's a really good way of writing it. Yeah, that f of x is d of x times x minus c for a zero. Thank you. Or I guess maybe a better way to write it, where c is a zero. That's much more succinct. All right, questions? Yeah. Yeah. Yeah, so this one here is the idea of if we know a zero, then we can write it as x minus c times some other function d of x, where d of x is what we get by doing this division of f of x divided by x minus c. So technically, this is kind of all the factor theorem. It goes in both directions. So if we divide by an x minus c and get a remainder of zero, then it's a factor. And also, if our equation can be written in this way, then it goes backwards as well. Think of like this as the context. This tells you like what d of x actually is. This kind of implies the whole like remainder of zero thing. And this is like the overall conclusion, which is that we can write our function as a polynomial times that zero that we just found. Other questions? All right, we got about 10 minutes left. We have the 2.4, 2.5 with the factor theorem and the remainder theorem. You should be able to do through the rest of 2.4. So I think it's through number 9, if I'm not mistaken. And then we'll wrap up 2.5 tomorrow, at least, is the game plan. I guess we'll see how well we can do that. But to that end, first 9 problems for that point of extra credit, we'll say due at the end of next class. And you guys have the rest of this time to work on that class. Sure, you think you can do that? Well, we should have a class period where there's a longer. It's just smart. Just with the